Hello everybody, this video is going to be about weak acids and bases and the types of calculations that we have to do with them since they're not quite as straightforward as our strong acids and bases. So what do I mean when I say that they are weak? What that means is that they do not completely ionize in water. Only a tiny bit is going to be dissociated. That makes our calculations a little bit more complicated. What's going to happen is we're going to be thrown right back to the equilibrium chapter. Dissociation is reversible, which means there's a forward and a backwards reaction taking place, which means it's equilibrium. We're going to need equilibrium constants, we're going to need expressions, we're going to need ice tables in order to get our concentration of hydrogen ions to be able to calculate our pH. We can't use our simple negative log calculations. We can't just jump right in and do that because we have to first determine how much of the acid will dissociate and then use that to be able to do our calculations. So we aren't actually learning anything new. All we're doing is we're applying our ice tables to an acid-base problem first. And then once we know our concentration, we proceed with our normal pH calculations. So we're really just pushing these two chapters together. That's really all we're doing. So first we have to make sure that we understand that the equilibrium constant is a generic constant. It could be a concentration, it could be pressure, it could be something called KSP. So if you are doing acids and bases, we're going to use a Ka to tell people that it's for acid, or a Kb. There we go. It's still products over reactants. We still use our coefficients as our exponents. We still ignore solids and liquids just like normal. This time, because it's an acid or a base, our ions will be our products and the undissociated one will be what our reactant is. Here are some generic equations we like to use to represent the acid dissociating into its ions or a base dissociating into its ions. Now, yes, I know that's kind of using the simple definition of acids and bases, but it's just supposed to be a generic equation to give us an idea. So let's do a practice problem. First, just for a little bit of practice, I would like you to try to identify your acids and bases and conjugates for this equation first. Let's just do a little bit of extra practice. All right, so if we look, this molecule here, our acetic acid, is going to be donating a proton, so that is the acid. The water is accepting it, that is the base. The base turns into a conjugate acid. The acid turned into a conjugate base. So now let's write our Ka expression. You're going to want to put your products on the top, your reactants on the bottom. The nice thing is all of the coefficients are ones, so we don't have to worry about exponents. But we do have a liquid here. Don't put the liquid. Okay, do not put that liquid. Our Ka value looks like this. It is going to be important that you label if it's Ka or Kb, because sometimes we use both and we need to know which one we're talking about. So please make sure that you're using your little subscript letters to tell us. AC is representing, all the other part of the acetate. We like to abbreviate it sometimes. All right. Now, a weak acid should have a pretty small Ka value because we don't have very much dissociated. Our numerator should be pretty small. most of it should stay together. So our denominator should be pretty big. So we should end up with a pretty small number. That's telling us that the equilibrium lies far to the left side. It is reactant favored. Not much is going to dissociate. That's why it's a weak acid. These acids should have a Ka that's less than 1. Sometimes they're incredibly small. That's going to give us a very, very small concentration of hydrogen ions, which is going to give us a low pH when we plug it into our equation. Let's look at bases next. Basically the same thing. I use a Kb instead. My equation looks like this. My base is going to take a hydrogen off of the water. And now I have a hydroxide floating around. So I'm going to have my products on the top and my reactants on the bottom. And weak bases should have small Kb values. That's telling me that most of it is going to stay like this. It's shifted towards, it lies to the left. It's reactant favored. Not much has dissociated. I don't have very much hydroxide floating around. That's what makes it weak. They should have a Kb of less than 1. That's going to give us a really low concentration of hydroxide. So when we do our pH calculation, we end up with a pretty large number for our pH. So there's a nice little graphic that shows you kind of the relationships here. As your acid gets stronger, your concentration of your hydrogen ions go up and your Ka value goes up. That means you will have a lower pH because remember it's that negative log calculation, we get a low number. If our base goes up, we're going to have a larger Kb. Our pH number goes up, which means we have a lower concentration of those hydrogen ions. I really like this one because it's so simple. I think this graphic is pretty helpful. Just really basic, arrows up, arrows down. All right, let's do a calculation with these weak acid-base problems. So we have 1 molar of our acid. Calculate the equilibrium concentrations of all these pieces and the pH if the Ka is 1.8 times 10 to the minus 5. What you have to do is recognize that this is not a strong acid. Acetic acid is weak. I can't just do my normal pH calculation. I cannot do negative log of 1. That is not correct. Not much of this is going to dissociate. I do not have a lot of hydrogen ions present. So what I will need to do with this equation is create an ice table. I will have to write a K expression, A because this one's an acid, or maybe B. If the reverse reaction was happening, right, we would use a Kb. Remember the opposites, right? Opposite of Ka is Kb. Forward is an acid, reverse would be a base. Then you're going to use the quadratic formula if necessary, or the 5% rule. You cross your fingers and hope it's the 5% rule. Once you find your X value, once you know how much hydrogen you have, then you solve for pH. Or maybe you were solving for a hydroxide and now you're going backwards, right? So now you would do a POH. So let's do this. Let's get our ice table set up. We have our equation along the top, and you might notice that I did not include the water. Water is a liquid. Remember, it's not going to change anything, right? We don't put it into our ice table. Some people like putting the water in a column and then just putting like a slash through each box, or NA for not applicable, or something like that. So when we start, our initial concentration of our acid is 1. When I start, I don't have any hydroniums, and I don't have any of my conjugate base. None of it has been created yet. The nice thing here is it's a 1-to-1 ratio for everything, so it's just going to be losing some of our acid, making some of that, and some of that. So our equilibrium will be 1 minus x, and x. Now, is your Ka value 1,000 times less than what you started with, or even smaller? Yeah, so 5% rule should work. So ignore the subtraction here, just say 1. Compared to what we start with, not much will change. Over here, you're going to leave the x's, because compared to 0, it is a decent change. Next, just like we used to do, we're going to set up a K expression, a law of mass action. So what we're going to do is we're going to have our Ka expression, products over reactants. We were told what our Ka is, and we're going to plug in our info from our ice table. Why don't you take a minute and just practice, get your value for x. All right, you should have gotten this. Not very big, right? Just a teeny tiny bit gets made. Just a little bit is dissociating. So let's put it into our ice table. Let's get an actual answer. Remember, this is just going to stay a 1. We don't care. It's too small to worry about. Our sig figs wouldn't let us go out enough decimals to matter, would it? By the time we rounded, it wouldn't even look like anything changed. But over here, that is a decent difference. Now you're going to be good, right? You're going to double check that your 5% rule worked. Was X less than 5% of the 1 molar that you started with? Yeah, it was only 0.42%. It was just a teeny tiny bit. Not much to worry about at all. 5% rule was totally fine to use. The problem here is everybody forgets that the problem is not finished. The difference between the equilibrium problem and the acid-base problem is, well, we need the pH now. We're not finished. You have your concentrations. Now you can start the acid-base part. All that work was just to find what to start our calculation with. Now solve for the pH. Remember, pH will be log of the hydrogen concentration. We found that. Remember, we found our X value. We figured out what that was. It wasn't 1 molar. It was just this teeny tiny bit breaks apart. Punch that in your calculator, and you get 2.37. Now compare that to if all of this had dissociated. If the entire thing was strong and it all came apart. Instead of this little teeny tiny amount and a pH of 2.37, your pH would be 0. That'd be crazy, right? That's way different than this. So while this is a pretty low pH, it's still not nearly as low as it could have been because this is weak, not much dissociates. All right. Why don't you try this one? You try to fill in your ice table. I'll give you a minute. Pause the video if you need to. You try to fill in this ice table. Try to get all the way down to the 5% row and get that filled out. All right. Our initial concentration here was 0.01. We didn't have any product to start. Once again, it's kind of nice. It's a 1-to-1. Remember, we left the water out because water is a liquid. We don't care. Equilibrium will be initial minus the change. Over here, we have x and x. 5% rule. Is this 1,000 times smaller than this? Ignore the minus portion. Now it's time to get our expression and start plugging things in. So now set up your KB expression and try to solve for x. Pause the video so you have time to do that. All right, our KB is going to be products over reactants. We're going to leave out the water because it is a liquid. This is our base on the bottom, right? And this is its conjugate acid. The water was our acid, so this hydroxide is our conjugate base. It's good to practice that. Just randomly, just see if you can do it in your head. We plug everything in from our ice table, we solve for x, and we get our final answer. Now it's time to plug that back into our ice table. It feels like we're done, but we're not. You cannot forget to do the rest of the problem, pH calculation. There's a little bit of a trick here. You don't have the concentration of hydrogen ions, do you? This was a KB. You calculated OH. Your X value is the concentration of hydroxide. So, depending on what route you like to take on your little pH square, right, you can go different directions. I personally like to find the POH, and then I like to use the fact that pH plus POH is 14. So I just rearrange and I solve for my pH. And I can see it is basic, isn't it? Which makes sense. I think that it's really good to remind yourself that this weak acids and bases are the same things you've been doing, okay? We're just squishing together equilibrium and then finishing it up with some acid-base topics, right? We're just mushing those things together, okay? Acid-base is huge in AP chemistry. So one of the reasons we like doing this topic at the end of the year is because then it will be nice and fresh in your brain when you start AP Chem next year. So do a really good job practicing on these ice tables and on these acid-base calculations. And I think it will get you off to a really good, strong start in AP Chem. All right, everybody, that is it. I hope that was helpful. Bye.